So I hope you enjoyed the previous video or the cartoon about quantum physics. And I hope it brought up some curiosities with you on why things are the way they are. There were some mistakes in that video which we could talk about later, but interesting enough, it really brings up something that a famous French physicist named Louis de Broglie brings about. So remember now, we're in this quantum world where physicists are arguing, is light a particle, is light a wave? We have Einstein who quantized, and with Planck and all that, who quantized a wavelength and said, hey, waves can act like particles. Well, de Broglie comes around and says, well, if waves can act like particles, maybe particles can act like waves. So, with his tongue firmly in cheek, de Broglie suggests that perhaps baseballs or electrons moves like waves, which means they're going through crests and troughs. De Broglie figures he can make an equation to calculate the wavelength of a baseball, for say. So let's look at this here. So de Broglie figures we can make an equation for the wavelength of a baseball or electron or anything like that. So using Einstein's theory of relativity on how we are able to find out that a wavelength has momentum, he reversed it back and said, well, a wavelength then is Planck's constant. Remember this? We've been using it a lot lately, divided by momentum. So a quantized thing divided by momentum. Then he said, well, momentum is equal to mass times velocity. So wavelength is equal to Planck's constant divided by mass times velocity. Now mass is a very, very small, tiny thing. So if we look at a baseball has quite a bit of mass there compared to an electron, and it has a velocity. Now if we divide this together, we end up finding out things have a very, very small wavelength. So once again, we had Einstein's theory of relativity equals mc squared, or the more complicated way of writing out is this, which helped us to find out that momentum is energy divided by the speed of light, which then helps us to combining with the photoelectric effect, remember with Planck's constant, black body radiation and everything like that, comes up into here, and we combine that our wavelength is equal to Planck's constant divided by momentum for a photon, which then means a wavelength can have a particle, can have a wavelength. Sorry, a particle may have a wavelength. And this was de Broglie's hypothesis. Now this was very, very interesting at the time because now we're really getting into the quantum duality. Particles can be waves. Waves can be particles. Depending on what we're using it for, we do calculations for one as a particle, one as a wave. As a matter of fact, this became so confusing for some and so unbelievable that a famous Nobel laureate physicist named Max von Loo even stated that if de Broglie's hypothesis about electrons being also waves turns out to be true, he will quit physics. Well, it turns out his hypothesis was true. So here is our first example. What is the de Broglie wavelength of a 0.1 kilogram baseball moving at, let's say, 20 meters per second? So we know that the mass of the baseball is equal to 0.10 kilograms. I also know my velocity is equal to 20 meters per second. We are trying to figure out what is my wavelength. So using this, I'm going to go, my wavelength is equal to Planck's constant divided by my mass multiplied by my velocity. So Planck's constant is 6.63 times 10 to the negative 34 joules seconds, and we're going to divide that by 0.10 kilograms multiplied by 20 meters per second. And that's going to end up giving me 1.3 times 10 to the negative 31 meters for my wavelength. So let's look at our second example. It says, what is the de Broglie wavelength of an electron that has been accelerated from rest through a potential difference of 50 volts? So for this one here, we know my volt is equal to 50 volts. That's my potential difference. We know my charge of an electron is equal to 1.6 times 10 to the negative 19 coulombs. Now, there's not much more we know here, but what we are trying to find out is my wavelength again. But for this here, we could also look at energy, because we know momentum and wavelengths are related to energy. So energy is equal to question mark. So looking at that, I know my energy is equal to my charge of an electron multiplied by the volts. Now this is also energy is equal to, if you remember from units past, energy for this, we use this, we're accelerating it, so we're going to find my velocity at the end, and that is kinetic energy, which is 1/2 mv squared, mass times velocity. So now we could solve for my velocity for my main formula here, where we have lambda is equal to Planck's constant divided by mass times velocity. So velocity is the key thing we want there. So I'm going to isolate for velocity, and that's going to give me the square root of 2 multiplied by the charge of an electron multiplied by my volts divided by my mass of an electron. So I continue this here, and I'm going to plug in my unit or my numbers, and I'm going to end up getting 2 multiplied by 1.6 times 10 to the negative 19, and that's coulombs, and then we're going to multiply that by 50 volts. And that's all going to be divided by my mass of electron, which is 9.11 times 10 to the negative 31 kilograms. Now, that's going to end up giving me a total of 4.19 times 10 to the 6 meters per second. Now that I have my velocity, I could use this way back up here to find my wavelength. So my wavelength is equal to Planck's constant, which is 6.63 times 10 to the negative 34 joule seconds. And that's going to be divided by my mass of electron, which is 9.11 times 10 to the negative 34 kilograms, or to the negative 31, not 4. 31 kilograms multiplied by my speed, which is 4.19 times 10 to the 6 meters per second. Okay, I'm going to plug that all in, and I'm going to end up getting 1.74 times 10 to the negative 10 meters. And just double check, I think I have the right significant digits. Oh, we're going for 50. So that's essentially 1.7 times 10 to the negative 10 meters is my answer for my wavelength. So if I look at that, this electron has a very small wavelength, although it is still there. So now let's go over some provincial diploma questions. Our first question is, we have a beam of electrons is directed at two narrow, closely spaced slits. Each electron passes through the slit, causes a tiny flash of light on the fluorescent screen. After many electrons have passed through the slits, the distribution of the flashes on the screen shows up a double slit interference pattern of bright dark lines. So here we go. Here is my electron source shooting through the double slits, and we get an interference pattern of bright lines. Kind of what we learned from de Broglie and the quantum physics. So the probable distribution will be which one? For the first 20 electrons. So here is Y, Z, and X, and we're looking Y middle, Z, and X. So we're looking at this, and with the distribution, remember, it's going to now look kind of like a wave. So in this case here, if it's looking like a wave, my answer is going to end up being obviously B, because that is the closest to a wave. Let's look at my next question here. It has electromagnetic waves have a frequency of 1.3 times 10 to the 13 hertz. The momentum of its photon is what? Well, we know momentum is equal to Planck's constant divided by lambda. So we also know that the speed of light is equal to frequency multiplied by wavelength, which in this case here, we could isolate for wavelength is equal to the speed of light divided by frequency. So I'm going to substitute this in for lambda, which is going to end up giving me Planck's constant multiplied by the frequency divided by my speed of light. So I end up with 6.63 times 10 to the negative 34 joules seconds multiplied by my frequency, which is 1.3 times 10 to the 13, and that's second arc seconds. And we're going to divide that all by my speed of light, which is 3 times 10 to the 8 meters per second. Now, after this is going to end up giving me a total of 2.873 times 10 to the negative 29, and that's kilograms meters per second. So my answer for this one here is going to be B. So here's my next one. I want you to pause the video, see if you could solve it, and then we're going to go over why. So in this one it says, if each of the following particles were traveling at the same speed, the particle with the greatest de Broglie wavelength would be the, well, if we're looking at the same speed here, and my de Broglie wavelength is equal to, we're going to have that over momentum, Planck's constant over momentum, which is equal to Planck's constant over mass times the velocity. So looking at this here, this mass is a big thing. As the mass decreases, my wavelength will actually increase. So which will have the greatest wavelength? So in this case, I want the smallest mass, and that's going to be my electron. So my electron will have the biggest wavelength. Because as we decrease our mass, we're going to increase our wavelength. If we increase the mass, we're going to decrease the wavelength. My next question here, I want you to pause, see if you answer it, and then I'm going to go over it. So it has a photon's momentum will decrease when it's, well, what happens here? So what if its speed increases? Well, let's look at this again. Momentum of a photon is equal to Planck's constant divided by the wavelength. Right? Same idea. Now, we also know here that momentum is also equal to energy divided by my speed of light. Okay, because energy is equal to, from our formula sheet, is equal to the momentum multiplied by our speed of light. So let's look at all of these here. These are a few momentum things. So speed increases. Well, we also know here that momentum is also equal to mass times velocity. So speed increases, that's going to increase my momentum. Energy increases. Well, momentum is equal to energy divided by speed of light. So if my energy increases, that will increase my momentum. But it says energy decrease. Will that decrease? Yes, it will. Let's try the other ones. Frequency increases. So if I increase frequency, well, this is the same as Planck's constant multiplied by frequency divided by speed of light. If we increase my frequency, that's going to increase my momentum. So that's not true. The wavelength decreases. Well, if I decrease my wavelength, that's going to increase my momentum. So that's not true. So B is my only answer.